Okay, welcome to lecture here. We'll get started in just a sec, continuing on where we left off last week. So we should be in chapter 9, so where we left off. Okay, so last time we were talking about chapter 9, and we're talking some intermolecular forces. And just a reminder, some of those intermolecular forces that we talked about again, the intermolecular forces are the forces that hold one molecule basically together with another. So, for example, the bond or sort of the force that holds one water molecule together with another. And things like that are, there's basically three types of intermolecular forces. One is known as dipole-dipole interaction. Dipole-dipole interaction, as we talked about, is between basically two polar molecules that do not have the ability really to hydrogen bond. And basically, because they are polar, they have a positive side and a negative side. And it's the positive side of one atom or molecule, positive side of one molecule that is attracted to the negative side of another. And that's basically what keeps them sort of together. And basically, all those intermolecular forces, as we talked about, essentially are that sort of positive negative attraction that occurs. So when you have sort of a polar molecule and another polar molecule, again, that sort of positive and negative attraction that will occur. A special type of sort of dipole-dipole, which is known as hydrogen bonding, and that is typically the force that will hold a polar molecule that has the ability to hydrogen bond together. And remember that basically the ability to hydrogen bond happens when the hydrogen is attached to a very electronegative atom like nitrogen, oxygen, or fluorine. Those guys have the ability to hydrogen bond. So something like water, which has that OH bond in it, again, has that ability to hydrogen bond. That hydrogen is attached to an oxygen. It's also a polar molecule, again, having a positive side and a negative side. So the positive hydrogen in one would be attracted to, say, something like the negative side of an oxygen in another, and they'll come together. And lastly, there's sort of dispersion forces. Dispersion forces are really the intermolecular force that nonpolar molecules basically will use together. And they're really sort of temporary type forces because something is nonpolar. It basically means it has an even distribution of electrons. Essentially means that it's really doesn't have a positive side or a negative side. And what that means is because of that, it has to rely on these sort of temporary forces that can occur. So there's a couple of different ways that we talked about that sort of that temporary sort of charge could occur. But strictly speaking, between two nonpolar guys, that's most likely going to happen through sort of an instantaneous dipole, sometimes called. And that's a result of basically the electrons, say, in one nonpolar molecule, basically moving to one side of the molecule versus another. And when it does so, obviously the side that the electrons sort of travel to is going to become more negative because it has more electrons hanging out there. While obviously the side where they kind of went away from will become more positive. And what that does is essentially creates a temporary separation of charge in a nonpolar molecule. And if that nonpolar molecule, as we talked about, sort of next to another one, that will cause the electrons in the other one to sort of shift locations. And when that does, that one now also gains sort of a temporary positive side and negative side. So what happens sort of in dispersion force is a lot of times when you're dealing with nonpolar. Nonpolar is essentially they both sort of at some point gain this temporary positive and negative side, and that allows them a place to basically interact with each other and come together and bond. So in terms of all three of those, dispersion forces are pretty much the weakest because they are sort of temporary sort of bonds that occur between nonpolar guys. And the sort of strongest out of all three of those is hydrogen bonding, with dipole sort of being underneath hydrogen bonding in terms of strength. And that's because dipole and really hydrogen bonding, which is really part of dipole, in those situations, because they involve polar molecules, as we talked about, polar molecules have a fixed positive and negative side to the molecule. So no matter what the situation is, there's always going to be that positive side and negative side. They will never sort of lose that. So they're really always ready to sort of bond to each other. And that's different than in a nonpolar molecule. In a nonpolar molecule, they have to sort of wait for these electrons to sort of move and all those type of things. They don't always have a positive side and a negative side, and that's why it's a very temporary sort of attraction that occurs. And because it's temporary, it's a very weak sort of attraction that occurs as well. We then also talked about towards the end adhesive, cohesive type forces. And those are the forces, for example, that are responsible for things like the meniscus that we see in liquids when we put them into glass containers. Again, if the force between, say, the water molecule and the glass container is stronger than the force between the water molecule and the water molecule, that's why we sort of see that rise that occurs inside the glass tube and that kind of curvature of the liquid that gives us that sort of classic U shape, if you will, for the meniscus. And it's not always the case. We can have the forces between the molecule being stronger than, say, the glass tube. And that actually happens with mercury, I think was the example we saw. In that case, the mercury attraction is stronger than the attraction between mercury and the glass tube. And what ends up happening is the mercury kind of goes down on each other, and you get sort of that inverse meniscus that basically occurs. Any questions on any of that? So I think this is about where we left off here, if I'm not mistaken. So let's talk a little bit about vapor pressure and sort of what's going on with that here. So vapor pressure is basically the tendency, is basically what happens when we have sort of a gas over a liquid component. And when we have a gas over a liquid component, obviously it's because there's a gas present, there's going to be basically gas molecules. And that's basically what's causing the vapor pressure that we sort of associate, or what vapor pressure really is. And one sort of idea that's important is basically the tendency basically of a liquid to vaporize is what's known as volatility. And some liquid that's very volatile means that it will go into the gas phase relatively easy. And that means basically they'll just kind of very quickly go from liquid to gas and produce a lot of gas. Increases with temperature. So when we talk about liquid, say in an open container, it will start to evaporate at some point. And that's because really when you have a container and you have something to write with that you put somewhere, there it is. All right. So when you have, say, a liquid in a container, and really at the surface of any liquid, you really have that process of guys jumping out of the liquid, going into the gas phase. And you have kind of slow moving gas molecules, which then will sort of drop back into the liquid phase. So really at the surface of the liquid, you sort of have that process kind of happening and them going really back and forth. And the problem with, and what sort of happens, for example, if you put a liquid in a container and sort of leave it out for a while, when we have this process of the liquid going into the gas phase, you also have air, which then can push these gas molecules sort of away from, say, your beaker or whatever it may be, your tube. And what will eventually happen is you're losing all these guys that are escaping the liquid. You don't have as many guys then coming back into the liquid. And eventually what happens, right, is the kind of liquid level starts to go down and basically evaporate. That's also what happens, right, when we kind of spill something or gets a little bit of water, say on a counter or something like that, or in the cement or whatever it may be. And the difference with that, right, is it's able to really spread out. And unlike in a beaker or a container where kind of the bottom water molecules, right, are protected from the surface, here, and when you spill something right on the sidewalk or wherever it may be, the entire thing's sort of exposed to air. So all the way around this guy, you pretty much have these guys escaping into the gas phase. And again, obviously, these are all exposed to sort of air, and that allows or sort of accelerates the evaporation process that we sort of see. Again, it takes much longer for something like that to happen if you put a whole bunch of water into a container, again, because really only the surface water or liquid, right, is sort of being exposed to that. And the guys at the bottom sort of has to wait for all these guys up on top to sort of go away until they kind of start evaporating. While here, obviously, greater surface area is being exposed and basically kind of accelerating that evaporation basically to occur. Now, when we do have sort of that process that occurs at the liquid, like I said, with these gas molecules that are sort of escaping up here, because there is sort of gas molecules above that surface, I'll just draw gas. These gas molecules are going to create a sort of pressure associated with that. And that especially happens when we, say, put a top on the container, right? When we put a top on the container, same thing's happening. Our liquid are coming to the gas phase, but now really that gas molecules can't escape. So it's going to kind of maintain that pressure above the liquid. And again, that's sort of our vapor pressure. Liquids with very high vapor pressures are said to be volatile, and they evaporate really quickly. And that means in order to create the pressure above the liquid, that means you need to have a lot of gas that's above the liquid. In order to get a lot of gas in sort of the liquid phase, that means a lot of the liquid molecules has to go into the gas phase, and thus it would start to evaporate very, very quickly. Now, the vapor pressure of a liquid at a given temperature is determined by the intermolecular force that's present. And obviously, the higher the intermolecular force, or the larger the intermolecular force, or stronger the intermolecular force, the lower the vapor pressure you would assume. And the idea behind that is the stronger the intermolecular force, say between this molecule and this molecule, the stronger that force is, the longer these two are going to stay together. And remember, in order to get into the gas phase, they need to break apart from each other. So the stronger it is here to keep them together, the lower the vapor pressure will be, because again, you will have less gas molecules being able to be produced. Less gas molecules means less pressure. Less pressure means basically less vapor pressure above that liquid. Now, when we look at, again, a sort of solution in a closed environment like this, we don't obviously get that rate of evaporation that occurs. And that's really because by putting a lid on it, if you will, we basically have now prevented these molecules from escaping, right? They can't get kind of pushed away by air, and that's not going to obviously accelerate the evaporation process. But what we will notice, though, is if you look at sort of the liquid volume here versus here in the two sort of flasks here, is there's a little bit of a difference. So although they can't escape because of the lid here, what happens is when we first put the liquid in there and sort of close the lid, we have a greater rate of evaporation that occurs, right? So we have this greater rate of guys basically jumping out into the gas phase. Again, they have nowhere to go, so eventually some of these guys are going to start dropping back into solution. And at some point, they will reach equilibrium. And basically what equilibrium means, as we might have mentioned a couple of times, but just to remind, is equilibrium basically means that the rate of one direction equals the rate of, say, the reverse direction. So as quickly as they could kind of jump out of solution, they just as quickly can come back into solution. And at some point, the rate at which they come out will be equal to the rate at which they come in. And usually what will happen is because you have that sort of greater rate of evaporation to begin with, you'll have a little bit more gas molecules than you did liquid. And that's obviously going to make the liquid volume come down a little bit. And what we see is once it reaches that equilibrium, basically the level of the liquid in each of them will overall kind of go down before it hits that equilibrium. And again, that's just because before we put it in, we have kind of no evaporation. As soon as we put it in, we get that evaporation to occur. The liquid level will come kind of down a little bit because some liquid molecules have escaped into the gas phase. So one way you can sort of calculate sort of something like that, the vapor pressure, is through this equation here. This is the Clausius-Clapeyron Equation. And it's a natural log of the pressure, the vapor pressure here at temperature 1 divided by the vapor pressure at temperature 2 equals delta H of vaporization. This is the enthalpy. We don't talk too much about heat, but enthalpy is delta H. And that's basically the heat of a reaction. And the delta H of vaporization, when we see that number, is the energy needed to go from the liquid phase to the gas phase, or backwards, the gas phase to the liquid phase. And this all occurs, by the way, just so you know, hopefully, this all occurs at the boiling point, and that occurs basically at the same temperature. So if you're going from, say, liquid to gas or gas back to liquid, for example, 100 degrees is the boiling point for water, and that's when that happens as you go from liquid to gas or gas to liquid. So the delta H of vaporization would be the same value for something like water, going no matter which direction you go. But the difference is the sign. I think we might touch upon it as well. But in general, if the delta H value is negative, it means that the overall process was exothermic. And that means, again, that heat and energy has been released. And if the delta H is a positive number, it means that the overall process was endothermic, which means as a whole, heat and energy was absorbed. The R here is actually the gas constant in terms of energy, and that's our, like we see here, our 8.314 version of the number. Temperature is in Kelvin, so each of these. So let's take a look at how we will calculate something like this. Or there's the answer right there. So the vapor pressure of water at 25 degrees is 23.8 torr. The heat of vaporization is the delta H of vaporization. That is what it's talking about there, is 43.9 kilojoules. And we want to calculate the vapor pressure at 65 degrees Celsius. So again, here we would use the natural log of our pressure at T1 over pressure at T2 equals, again, our equation that we have here, our delta H of vaporization over R. Our 1 over T2 minus 1 over T1. So we do have to do some conversions. So kind of like most things with temperature, we do need to convert them into Kelvin. So if we call T1 our 25 degrees, that's going to give us 298 Kelvin. And since I called that T1, my P1 will be 23.8 torr. That means that, let's see here, the vapor pressure will be, the one I'm looking for will be P2. And my T2 would be 65 plus 273, gives me 338 Kelvin. All right, so if we put this in, we get the natural log of our P1, which is 23.8, divided by our P2, which is what we're looking for, equals our delta H, which is 43.9. Now, you do have some unit issues here. This is in joules. This guy's in kilojoules. So you do need to do a conversion. So I'm going to take that 43.9. I'm going to times it by 1,000, and that's going to convert it into joules. And again, I do that because of 8.314 joules per Kelvin per mole. Again, because that is R and it's in joules. Otherwise, again, you will be off by a factor of 1,000 if you don't do that conversion. You could convert the joules to kilojoules and do it that way if you like as well. All should come out the same. T2 is 338 minus 1 over T1, which is 298. So let's do some cleaning up here of our right-hand side. So we're going to take 1 divided by 338 minus 1 divided by 298. We're going to times that by 43.9 times 1,000. We're going to then divide it by 8.314. And if you do all that, that will get you the natural log of 23.8 over P2 equals minus 2.0969, some numbers. To get rid of the natural log, what you need to do is you need to take the E of both sides on your calculator. So on your calculator, you take the E to that and the E to that guy as well. When you do the E to the guys on the left, it just becomes 23.8 over P2. And if you do the E on the other side, you end up with 0.12283. You then need to multiply the P2 to the other side and then divide. So if you do that, you will get 23.8 equals 0.12283 P2. Divide this back to the other side. Those guys cancel. These guys end up with about 194 torr, as you can see here. So this is an equation where you could use, obviously, to calculate, as you can see there, are really four things. You would most likely be given, obviously, you would most likely be given three of the four things, very much like in this problem. Probably, to be honest with you, you could do it either way, but it might be easier. Might be easier to actually plug the numbers in and kind of reduce it down. Then you're kind of left with not a lot of numbers and stuff to, you know, because you then would have to figure out the E of the right-hand side if you didn't plug the numbers in. So I probably would plug the numbers in, and then it makes it a little bit easier to kind of rearrange at the end to solve for what you're looking for in terms of the, say, P2 for this case. And what we see here as well is we do see that the vapor pressure definitely increased with temperature, right? So at 25 degrees Celsius, the vapor pressure is 23.8, which means when we raised the temperature to 65 degrees Celsius, the vapor pressure went to 194, and it increased a lot. So that's also something that we know from the gases, right? If we increase the temperature, got a lot more movement of gases. Also, if we increase the temperature, that's going to allow a lot more liquid basically to go from the liquid stage to the gas stage, right? Everybody's going to gain more energy. They're going to have more energy to escape and go into the gas phase. And that's what we see here with the pressures. The pressure extremely goes up as the temperature goes up. And again, it's just, if you want to think about it sort of in a sort of easy example to think about is, right, is if you have a pot of water sitting on the stove, you're not going to get a ton of steam coming off of that, right? You turn on the stove and start to boil it or sort of heat it up, you start to see an increase in steam coming out of the water, right? As you're increasing the temperature and the temperature of that water gets higher, you start to see more gas molecules or water molecules have enough energy to escape the liquid part and start to create steam, which is basically kind of what you're happening in this situation. Any questions on that there? Okay. So then let's talk a little bit about boiling and some aspects of sort of what's happening with boiling. And so when we start to boil something, or by the way, boiling obviously occurs at the boiling point for most substances. And really that is when we get the transition that occurs from the liquid state to the gas state. Again, that transition occurs basically at the same temperature for those things. It just really requires what's happening in terms of energy. So those sort of transitions, you know, in terms of say going from solid to liquid, or liquid back to solid, or liquid to gas, or gas back to liquid. Again, this process are equilibrium processes, each of these things, and they do occur at the same temperature. It just, like I said, depends sort of on energy and what you're doing. If you are continuously supplying energy or increasing the energy, the process will occur in sort of this direction, right? You'll be going from solid to liquid or liquid to gas. And again, that's an endothermic type situation when you continue to kind of imply the heat in there, or energy. Opposite is true. If you take away heat and energy, you would be going in the opposite direction, which would be sort of an exothermic process. And in that sense, if you kind of take out the heat and energy, the gas molecules that are flying around are going to slow down. And basically when they come together, they're going to kind of clump into the liquid phase and then continue to sort of clump together into the solid phase if you continuously take out heat and energy. So when liquid water is heated to a high temperature, basically bubbles of water vapor form beneath the surface. And if you ever sort of took like a beaker of water, even like that example, if you're boiling some water for, say, making pasta or something like that, you see a couple of things sort of occur as you're sort of heating it, right? And as you're sort of heating it, probably if you ever notice, as soon as you kind of hit it with the flame, you'll see all these sort of little sort of quote unquote bubbles that basically form like super fast. And you go, well, it's not really boiling. Obviously, if you touch the water, it's still super cold. Obviously, it's not hot. And what that is obviously is not the water or the liquid, for example, bubbling. What you just did there is basically expelled a lot of the CO2 molecules out. And basically they're less soluble in a hotter solution. So as soon as you hit it, all those first like little bubbles that sort of pop out really quick are really not the solution. Boiling obviously is sort of that lower solubility of those gas molecules in that liquid that happens very quickly because you hit it with the heat really quick. And then they kind of disappear, and then you got to wait. And it's really not until you kind of see those kind of, I'll draw oversized bubbles here, these kind of really big bubbles that start to form underneath the surface, right? And basically, eventually what we see is these bubbles will work their way right to the top. And when they reach the top, obviously they can then pop, and the water vapor that's inside can now escape and create sort of the steam that we see at that point. And it's when those bubbles really start to form and we see them sort of making it to the surface that we could say that the liquid is really boiling. Before that happens, you may see some bubbles really start to form, but they may pop before they actually get to the surface of the liquid. And that solution would not be bubbling at that point, or would not be boiling at that point. And that's because really we can only get those guys sort of under the surface to form if the pressure inside that bubble is greater or equal to basically the atmospheric pressure. And that's because there's really atmospheric pressure pushing down. And these bubbles basically inside or not equal to that are going to basically pop before they get to the surface. So only these guys over here, for example, that inside here, they have a pressure is at least equal to atmospheric pressure. That's going to allow them to successfully sort of get to the surface. So at the boiling point, the liquid pressure of the vapor of the bubbles will be equal to or greater than basically the water and the vapor pressure that's basically out there, atmospheric pressure that's basically outside. And at lower temperatures, the pressure inside the bubble is lower and it basically will collapse. And that's when you start to heat your thing, you maybe see a bubble that starts to form and kind of pops. And, it's not really, again, boiling until you get sort of that rate of all those bubbles that are able to continuously sort of form and make it to the surface. And again, at what temperature something boils depends really on temperature and pressure. So, for example, the boiling point, sort of at sea level is 100 degrees Celsius. But if you sort of go, say, higher in elevations, it may actually boil at a lower temperature, right? So if you're in like Denver or something like that, you get to sort of boil at a lower temperature because of the atmospheric pressure. So you could even, as weird as it sounds, in sort of regular temperature, just drop the pressure a lot or change with the pressure a lot, and you can really affect sort of, water boiling because of the pressure that's associated with it. And we'll sort of see a pressure-temperature relationship a little bit later on in the next chapter, I think, as well. So, for example, something like a pressure cooker like that, it increases the boiling point. So, for example, instead of water normally boiling at 100 degrees, because of the pressure that's associated there, the pressure is very much increased. The boiling point actually needs to increase to about 120 degrees Celsius. And what we see here is, again, because this pot's under very high pressure, the vapor here basically will escape and be held above the liquid. And that increases the boiling point of that because it's going to take a lot more energy, if you will, for more gas molecules now to escape, again, because you have all this extra pressure pushing back down on sort of those bubbles as they start to try to boil. Thus, I guess a higher temperature perhaps cooks your food a little bit quicker. Again, as I talked about, sort of maybe in the Denver example, you lower the pressure, the boiling point will also decrease as well. So as odd as it may sound, boiling is actually sort of a cooling process that occurs in one sense. And it's a cooling process in the sense of, as we're sort of heating from the bottom, which is what we think about as boiling, it's got to be sort of a heating process. We're actually cooling from the top. And what that means is, as you can see sort of in this picture, as we start heating it, obviously it's gaining a lot of energy. But as all the steam and stuff sort of escapes, we're actually cooling or losing a lot of it from the water molecules that are escaping and basically coming out. So we sort of cool it from the top as quick as we sort of heat it from the bottom. And that's why if you've ever in the laboratory, for example, put a thermometer in, and if you ever looked at your thermometer, a lot of thermometers that you see in the chemistry laboratory, they top out about 101, 103, something like that. And people a lot of times concerned like, oh, wait, my thing is boiling. Do I have to worry about it? My thermometer rising way above 100 and breaking, basically. And you don't, because basically what happens is sort of this process here is sort of a cooling process that occurs. So basically, just as quick as you heat it, you're kind of cooling out the top of your solution. And what that's going to do basically is maintain, in theory, your 100 degrees Celsius as your boiling point. So it really shouldn't go way above 100. It shouldn't continue to heat at that point. It will basically reach sort of equilibrium. And sort of that idea of, as it goes from liquid to gas and gas back to liquid, you eventually will sort of hit a rate that's equal to each other. And thus it will sort of be able to sort of maintain that temperature of its boiling point of 100 degrees Celsius. And obviously, as we sort of escape these things, these are the process of evaporation, right? As we go from liquid to gas, that's evaporation, or sometimes called vaporization. And as I mentioned, that's basically an endothermic process. So heat and energy needs to be put in to do that process. Again, as everybody gains that heat and energy from that endothermic process, they gain enough energy basically to sort of completely break apart from each other and enter into the gas phase. And the opposite is true if we sort of remove the energy, as we talked about. If we remove the energy and energy is sort of given off, and that's an exothermic process, we will go through condensation. So as I mentioned before, basically, as they're flying around and they lose all this energy, they're going to start flying around a lot slower in the gas phase, and they're going to kind of clump together and kind of fall back into the liquid phase. And again, that's known as condensation. And as I mentioned, basically at the surface of a liquid, you basically have this occurring basically back and forth. So there is no difference that occurs there. Everybody's going in and out, in and out. And again, depending on sort of what's happening around there, you may see a great increase in the evaporation rate that basically will occur. So as liquids basically escape to the liquid phase, or escape the liquid phase, they take a lot of their kinetic energy with them. And the overall sort of kinetic energy of the liquid water is basically cooled. So basically what we're talking about here is, as these guys are basically escaping, they're taking a lot of their sort of energy with them as they escape. So overall, the liquid part here is losing a lot of kinetic energy, which is sort of cooling it down, if you will. As a result as well, when they sort of break free and everything, once these guys basically are able to kind of get into the air, if you will, they're definitely moving a lot slower than the molecules or gas molecules that are in the air. And as a result of that, they're basically going to be lowering the actual energy of the surroundings as well. And the kinetic energy of the air is actually cooled as well, because you have these fast moving air molecules that are now have these slower guys that had to break from hydrogen bonding and kind of get out into the air as well. Again, not moving as fast, and thus kind of cooling it as well. And this is sort of what happens, for example, sort of when we have water on our hand or our body, right, is we feel cold. And we feel cold because once that liquid basically hits our skin, the process of evaporation will begin. And where the water in that case will get the energy to go through evaporation is us. So our body heat, right, is going to increase the process of evaporation to occur. And as it does that, we're going to feel basically the sensation of being cold, right? Because we're losing some body heat going to the process of evaporation. That's why, right, when you get out of, let's say, a pool or something like that, or you've taken a shower, you have a lot of water on your body, you have a lot of evaporation occurring very quickly. And that evaporation is happening over a large area of your body, right? And you're losing a lot of heat doing that. And that's why you do feel cold when you do that. That's also sort of the process of why we sweat, right? When we sort of overheat, our body makes us sweat, and then we feel cooler in that sense, right? It allows us to sort of cool down as we lose a lot of body heat to obviously increase the process of evaporation of our sweat that occurs. So in that sense, evaporation is sort of thought of as sort of a cooling process. Now, sort of the opposite of that is our condensation, which is sort of thought of as a warming process. So condensation occurs when we get these slow-moving water vapor molecules that basically collide. So as they are flying around in the air, as we talked about, they're a little bit slower. They sort of stick together, and they basically fall back into the liquid phase. When they do that, these fast-moving water molecules will basically bounce off the surface, but the slower guys will basically come back down into the liquid phase. Hydrogen bonding is being made in that process, and that's an exothermic process. When we sort of make a bond, you have to get rid of some energy and to allow everybody to come together. So that's going to release some energy. In addition, those slow-moving water molecules, for example, in steam, have now left the air, right? So you have a greater amount of faster moving air molecules. So sort of the overall kinetic energy of the surroundings also increases, and condensation is a warming process. So a little bit of a more practical application is, again, if you think about something, for example, like when you do take a shower or a hot shower, when you take a hot shower, obviously that water is creating a lot of steam. And when that steam hits things that are basically kind of like colder surface, right? Like your mirror, right? That fogs up, right? And all that kind of stuff. The process of condensation is going to occur a lot quicker rate. And when it does so, it's going to give off the energy as those gas molecules basically go from steam to liquid water. And when it gives off those that energy, basically you're standing there and your body's going to pick up all that energy. And when your body picks up all that energy from all the steam that's going through condensation, you feel a lot warmer, right? So that's why when you take like a warm shower, you feel really warm. And then you shut off the water, and now you are stuck with a lot of water on you and not so much steam happening, right? And then the opposite process that we just talked about occurs. You go from feeling really warm to feeling kind of really cold afterwards. Again, because what happens in that case is the process of evaporation, like we just talked about, increases and you feel cold, as opposed to before that happens, you have a lot of steam present and you have a lot of condensation occurring and you're getting all this energy from that happening and you feel warm. These are always good life lessons to know what's happening, I suppose. So the process of doing this, again, just the phase change of a substance. And in particular here, looking at going from liquid to gas or gas to liquid, this is basically what happens with water here. This is liquid going to gas, so this is basically the formation of steam, right? Or water vapor, and vice versa, going from steam back to liquid. We make our liquid water. And again, this occurs all at the same temperature. So for water, 100 degrees Celsius is where this occurs. Again, the normal boiling point for water. And this is the heat of vaporization. And it really, again, as I mentioned, is the same value no matter sort of which way you're going. The only difference is really the sign. So as we talked about here, going from liquid to gas, it's an endothermic process. So the delta H value would be positive 40.7 kilojoules, which is roughly about 2260 joules per gram, give or take. And going the opposite way, going from grams to liquid, going from gas to liquid, again, it's an exothermic process. So exact same number, only difference is the sign is negative 40.7 kilojoules per mole. And that's roughly minus 2260 joules per gram. And if you're going to do a calculation, which we won't do very many calculations involving this, as I mentioned before, you'll do those calculations in 200B as they move this chapter to 200B, the sort of energy chapter. But when you do the calculation, again, you use basically the same value. It's just really the sign when you talk about heat and energy that tells you sort of what's happening in terms of exothermic or endothermic. So I think this is sort of what I was talking about when we get out of the shower there and all that good stuff. So we must go over that again. But again, that's why you feel cold in certain situations there and kind of warmer in other situations. Also sort of the same idea as those process of like those hot pads or cold pads where you can kind of break something and then it kind of feels cold, or you break something that feels warm. And basically when you do that, it either gives off an endothermic or exothermic type reaction. And that's why you do feel sort of those different feelings. So let's talk about what happens sort of in the other side of the spectrum in terms of going from solid to liquid, really, and liquid back to solid. And what's happening here again is as we go from solid to liquid, that's the process of melting. Like an ice cube starts to melt, and obviously going back the other way from liquid back to solid, again, it's the process of freezing. So as I mentioned before, going that solid to liquid route is endothermic, and going from liquid to solid is exothermic. And again, just like sort of evaporation and condensation occurs at the same temperature. So something like water, that's 0 degrees Celsius. By the way, if you're not dealing with water, It would be different temperatures. And that's the normal melting point or freezing point, for example, of water. And at this temperature, water molecules that are moving slowly can basically clump together and make ice crystals. Remember that basically part of the difference between solid and liquid state is they both are relatively close to each other, everybody. But the difference is in the liquid state, they still have the ability to sort of pass each other, the different molecules. And again, that's why liquids are fluid. But when we get to sort of the solid state, they no longer have that ability to basically pass each other or anything like that. And that's what we sort of associate there with our solid state. Again, in terms of sort of solid and liquid, for example, for water, it's really not until you get sort of above 0 degrees Celsius that you do have sort of liquid water that occurs. Again, not until a little bit below 0 degrees Celsius that you have really sort of ice or solid occur. Again, right at 0, you do have sort of both phases and happening together. So you have sort of like ice crystals sort of occurring at that point, a little bit of the liquid phase, a little bit of the solid stage happening at that point. And speaking of water, water is a little different than most compounds or substances in their solid phase. When water comes together in a solid phase, it creates all this kind of open area between the different water molecules when they come together through hydrogen bonding. And that gives water some unusual characteristic than most substances, as we've talked about, I think, before as well. But water basically in its solid form is actually less dense than in its liquid form. And that's the reason why right there is because, again, it creates all this open volume between the water molecules. And density, right, is mass divided by volume. So it has a larger volume, which means its density goes down, as opposed to in the liquid stage. It's the opposite there. It has a little bit larger, smaller volume and a little larger density in that case. And that's why ice, for example, will float right on water and liquid, right? And you put it in your soda, right? It floats to the top and all that kind of stuff, rather than sinks like most things in a solid state. And sublimation and deposition is the last sort of process that, you know, occurs between different phases. And a reminder, sublimation is going from solid directly to gas, kind of skipping the liquid part. And backwards is deposition. And sublimation, again, we basically skip altogether the liquid part. So for example, dry ice is an example of that. You have solid, it goes directly to gas, no liquid cleanup in the middle there. And deposition is the reverse process where we go from gas directly to solid. And, you know, for example, if you've ever seen a CD or a DVD or something like that, you know, it's all shiny and stuff like that. And that's sort of the process. Deposition is used to sort of put some of those metals on it to give it that sort of shiny appearance. And again, we skip the liquid part on that. In terms of heat and energy, the same idea as you go, say, solid directly to gas, that's endothermic. And if you go from gas directly back to solid, that's exothermic to do that. And basically, there's the heat of sublimation and the heat of deposition. And really, if you wanted the heat of sublimation, it's basically the heat of fusion, which is the energy to go from solid to liquid, plus the heat of vaporization. So the heat of fusion is back here with this guy, really. I think we'll see the number in a second. But the energy required to do this transition is the delta H of fusion. And that's the energy that's required to, again, do that transition in both directions. And for example, for water, as we will see, I think it's something like 6.02 kilojoules per mole, which is roughly 333 joules per gram, is the heat of fusion for water. And again, nothing happening in terms of temperature. This all happens at, say, 0 degrees Celsius for water. But again, it's just that energy to do that transition going from one phase to the next. So sublimation, which basically encompasses both of those things happen, go from solid to liquid, liquid to gas. It sort of happens all at once. The energy to do that is basically all those guys added together. And again, not to worry about too much about the calculation part, because again, I guess you just went forward there for a second here to do it. But again, we're not really going to do any calculations involving sort of heat of fusion, heat of vaporization, other than sort of that one that we saw where it would be given to you. And these values would be given to you if you had needed for that calculation. So this is, again, our delta H of fusion, which is the molar heat of fusion, or the enthalpy of fusion, but the heat of fusion is what it's called. And if you're just comparing the two, for example, basically, as I mentioned, the delta H of fusion, depending on what number you use, somewhere between 333 to 335 joules per gram, while the delta H of vaporization is about 2260 joules per gram. And you can see that in terms of energy of doing those transitions, as you can maybe imagine, the energy to go from liquid to gas is a lot more than the energy to go from solid to liquid. And that has a lot to do with sort of the intermolecular forces we've been talking about as well, and sort of what happens as you go from solid to liquid. And solid, everybody's pretty close to each other. In liquid phase, they get a little bit further from each other, but still relatively close to each other. But when you go from liquid to gas, you're going from a situation where everybody's close to each other to they've now 100% broke apart from each other. And to be able to 100% break apart from each other, they need a lot more energy to do so. And you can see by comparison here for water, it's about 333 joules to go from solid to liquid. A lot, but not a terrible a lot. But then you need to go about 7 times the amount there, about 2260 joules to go from liquid to gas. And again, in that case, what we're doing is completely breaking apart from each other. And again, takes a lot more energy to always do that transition, liquid to gas or gas to liquid versus solid to liquid or liquid to solid. And that's what we see here sort of on a heating cooling curve. This is ice, which is really the solid state. This is obviously liquid water, which is the liquid state, this kind of middle line. The top line up here is steam, which is basically gas. And we won't talk too much about heat, but maybe you might remember maybe Q equals ms delta T, which is specific heat. And then again, something you'll talk about in the next semester. But you use that when we are changing the temperature, but staying in the same phase. When we are dealing with the same temperature, but different phases, we are dealing with our heat of fusion and heat of vaporization. So this is 0 degrees Celsius for water, and this is where we go from solid to liquid. And this is where we use our delta H of fusion. We need to do any type of calculation with the energy. And this is going from liquid to gas and backwards, again at 100 degrees Celsius, as you can see. And this is where our delta H of vaporization basically occurs. And you can see that at both of those points, the line there is flat and plateaued. And again, we're not changing the temperature at those points. It is simply going from one phase to the next. And that's why it doesn't go up or down at those points. And that's why that boiling point there at 100 degrees is both where liquid to gas occurs and gas to liquid occurs. And why, if you look on the bottom there at 0 degrees for water, that is where both solid to liquid occurs and liquid to gas, liquid to solid occurs. Again, at the very same temperature. You could also see just, we talked about the numbers there, that the line going from liquid to gas is much, much larger than obviously the line that's going there from solid to liquid. And again, that's because it takes a lot more heat and energy to do that transition than it does down here. Any questions on that there? So now what we're going to talk about is sort of the relationship sort of between temperature and pressure, and sort of how it affects things like boiling points and what phase something's in. And to help us along with that is what is known as a phase diagram. And in a phase diagram, it basically will show several things. It will show basically the three phases. So it'll show, you know, where on the diagram something is necessary solid, liquid, and gas. It will also show the 6 interconversions among them. And the 6 interconversions is your solid to liquid, right? Your liquid to solid, your liquid to gas, your gas back to liquid, your solid directly to gas, and your gas back to solid, also known as what we've been talking about: melting, freezing, evaporation, condensation, sublimation, and deposition. Those are basically your 6 interconversions, all that stuff we've just been talking about. And you'll see sort of the temperature pressure values sort of associated with getting something, for example, to be in the solid phase or getting something to be in the liquid phase. We'll also see on there places known as sort of the triple point. And the triple point is the pressure temperature combination where all three phases are happening at once. So it's basically going to be sort of the pressure and temperature combination that if you had that particular substance, you would actually see both, all three things, solid, liquid, and gas, occurring all at the same time. Water has an unusual sort of melting point line. It's sort of a negative slope. And again, that accounts for ice being sort of less dense than liquid water. And some important parts on the graph that we will sort of see is the critical temperature. And the critical temperature, and we'll see it on the graph in just a second, is the temperature above where there's really no distinction between the liquid and really the gas phase or the vapor phase. So that occurs at the same point as really the critical pressure, which is the point where, again, there's also that no distinction between the liquid and the vapor phases. This is just sometimes in general comboed together as the critical point. So really the critical point on a phase diagram is the temperature pressure combination where you basically have something that has very similar properties to a liquid, but kind of flows like a gas. And that's what's known as a supercritical fluid. And again, it has properties like density is similar to liquids, but it will kind of flow very much like a gas. So let's take a look at a generic sort of phase diagram, some of the important sort of points on it. First off, usually going left to right on a phase diagram, or by the way, on the Y you have pressure, on the X you have temperature. But going from left to right is typically our solid, our liquid, and then our gas phases as you sort of come across. So if you go left to sort of right, those are the different phases. Now the transition as you go from solid to liquid is the process of melting. So we come across this way, it's melting, freezing, coming the other way, going from liquid to solid. This is what is sometimes referred to as the melting point curve. And again, it's that process where if you go this way or you go this way, you know, you're either going melting or freezing, depending on which way you go. We also have over here our vapor pressure curve. And we have the same situation. We're going from liquid to gas. So again, we have vaporization or evaporation as you go this way, condensation as you go back this direction, again, going from gas back to liquid. Now, sublimation, right, is the process where we go from solid directly to gas. So that's down here on the bottom left. And here you can see we're going directly from the solid phase right into the gas phase, which is sublimation, and backwards going this way from gas back to solid in that case, skipping the liquid altogether. Now, right here is our triple point, and this is the point where here is our liquid phase coming in, here's the solid phase, here's also the gas phase as well. And that's the point where you have all three phases basically happening at once. And we're talking about that critical point. This is where our critical temperature and pressure is over here. And above that is where we get our supercritical fluid. That again is our guy. As you can see here, this is really our liquid. And then it's just sort of like flows into the gas sort of properties over here. And again, this is where we have something that will sort of flow like a gas, but have some properties very much like a liquid, like density and so forth. And that's what we see happening in this particular case. So when we talk about normal, say, boiling point, melting point, freezing point, when we talk about normal pressures is 1 atmosphere. Yeah. So normal pressure is basically 1 atmosphere. So if you were asked a question like, where would the normal boiling point be? Which is, say, for example, on this chart, 1 atmosphere was here. You would come across and go, okay, boiling point, bad example, but we'll go right here, right before that dot. And that would be where our normal boiling point would be, right on where this line is. And then if you could draw much straighter than I did there, you could come down and figure out what temperature the normal boiling point would be. If you have the normal, say, freezing point, you would stop at this line, right? Because that's the transition between solid and liquid and solid. And again, draw a much better straight line than what I just did there. That was nowhere near straight, but we'll just make a bigger circle there. And that would give you your normal sort of freezing point in that case. So you could use this graph to figure out certain things. So for example, let's take a look at this. This is the phase diagram for carbon dioxide, which is basically dry ice. And when we look at this, what we see is our same things we just saw in the previous generic one. Here's our solid, our liquid, and our gas. That's our critical point over here, which is kind of cut off. And again, above that, we would go from liquid into, sort of our gas phase in that case. That's our triple point right here. This is where we have all three phases occurring, solid, liquid, and gas all together. Now, dry ice, as we talked about, is a substance that will go directly from solid to gas, skipping the liquid point. So why does that happen? Because if we look at this will explain it to us. As I just mentioned, normal everyday conditions is a pressure of 1 atmosphere. And if you look at 1 atmosphere and say 25 degrees Celsius, which is like a normal temperature, at 1 atmosphere, if we just draw the line straight, we're going from solid and now we're entering right into gas. Yeah. And gas all the way through here. And in 25 degrees Celsius, if you let dry ice expose to room temperature, it's going to end up being gas. We did not hit any liquid at all in that process. Also, why dry ice is super cold, right? It's very cold temperatures here, right? And it still remains cold in its gas phase as it's given off that, right? And then as it starts to warm up, it will eventually be all gas and everything will disappear. So when the solid's still there, we're at minus 78 degrees Celsius, right? Which is super cold, which is why you don't touch dry ice, right? Otherwise you burn yourself until it gets over here to here where you could touch it because it's all gone by that point at 25 degrees Celsius, right? No more room temperature. It's all pretty much, it was gone away and went through sublimation. So this is why something like dry ice will go directly under normal conditions from solid directly to gas, skipping the liquid part. Now, let's say I wanted to force the dry ice to go into the liquid phase. In order to force it into the liquid phase, I would need a pressure that's above, I think this is 5.1, which is 5 times normal pressure, right? And somewhere in this region, right, which is 72, which is way more, obviously, pressure, 72 times than normal pressure to force that dry ice to go into the liquid phase, right? So it has to get it at a pressure between these two. I would also have to get it a temperature above minus 56.6 and keep it, below a temperature around here to keep it into the liquid phase. And again, under normal conditions, dry ice won't do that because our normal pressures is like 1 atmosphere, right? So that's an enormous amount of pressure to try to force the dry ice going into the liquid phase. And obviously you would need the correct sort of temperature to do that, to kind of lay you out somewhere in this region, that pressure temperature. So again, any pressure temperature combinations would allow dry ice basically to stay in the liquid phase. But again, under normal conditions, that won't happen, because normal conditions, we're hanging out right about here, which obviously we normally would see dry ice becoming obviously into the gas phase. And at that rate, at normal pressure, there's nowhere along this normal pressure line that the dry ice would go into the liquid phase. Any questions on that there? All right. So why don't you take a second here and for each of these, based on the diagram that we just saw, which I believe was the dry ice one, so you can look at this one or the one on the other page. For each of these, figure out what phase these guys would be in. Would they be in liquid? Would they be in solid? Would they be in gas? They'd be in all three at each of these combinations. So just take a moment and sort of figure that out there, and then we'll talk about it. Okay, so let's take a look. So the first one is 20 degrees Celsius and 72.9 atmospheres. So again, my screen is kind of small, but 20 degrees is somewhere in this ballpark, and 72.9, I believe, is that top line there. And if we look at those two, so like it says, 20 degrees in this ballpark, 72.9, that puts us right there, hopefully at the liquid phase in that case. Next one is minus 56.7, which I believe is here, and 5.1, which is right there. And that is our triple point, which means that we actually have all three phases basically occurring at once. So the solid, liquid, and gas would occur at 10 degrees Celsius and 1 atmosphere. So 10 is, in this ballpark, and 1 atmosphere, somewhere in this region. And that again should, since this is solid, this is liquid, over here should be our gas phase, and this should be gas at that point. At minus 78.5 degrees Celsius, which is here, and 1 atmosphere, which is straight on up right there. That is actually on the line between solid and gas, which means you would have both phases in equilibrium with each other. Remember that if you do fall on that line basically represents the equilibrium between the two phases, and you would have both of them occurring. And lastly, here we have 50 degrees Celsius, which is over in this area, and 80 atmospheres, which is right here. Yes. So at 80 atmospheres, there's ballpark right here. That is our supercritical fluid, which is our guy that basically acts as both a sort of liquid and gas. Yeah, so at the critical point, somewhere in that critical point, technically you would be between liquid and gas. If you're right on that critical point, it would still be sort of attached to that line of between liquid and gas. So you would have both of those phases. If you're just above it, or where we just ended up with the very last one there, you would be at that supercritical fluid. It would probably be classified as, which is essentially something that is something that has basically both liquid and gas properties. There's no distinction. So sort of, if I just draw that part of the line, this line coming up here where the critical point is, if you're at the critical point or anywhere on this line, again, that's between our liquid and our gas, you would have both of the liquid and gas if you're kind of on that line. And technically, if you're at that point, it's still at the end of the line, so technically it'd be liquid and gas. If you're anywhere above that, they'll oftentimes be called a supercritical fluid like the last one. And again, it's not that you have sort of liquid or gas phase happening together. You got this guy that basically has properties of both. So it's sort of a merging of those two phases and would be probably called supercritical fluid. But if you're technically right at that critical point, you probably would still be considered both liquid and gas happening at that point. Other questions on that? So this is a phase diagram. You do need to know a phase diagram. You need to know where solid, liquid, and gas is in the phase diagram. You do need to know where the kind of where melting occurs, freezing occurs, sublimation, deposition, condensation, and evaporation occurs. You need to be able to answer questions like we just did here. You know, if it's this pressure, this temperature, what phase would you expect it to be in, and so forth. Any questions on that there? Okay. That is a skating blade, right? It's good. I'm not going to worry about that. Let's talk a little bit about water. We talked about some of its properties, but again, just to sort of reiterate some of these things. Obviously, water is a very important part of life. It's, you know, most of what the earth there is covered in. Most of the property of water is due to hydrogen bonding, right? So hydrogen bonding has a very strong intermolecular force, which is why water has a relatively high boiling point of 100 degrees Celsius. We also talked about the properties of sort of that hydrogen bonding, and sort of the consequence of that is, again, we do see sort of an unusual property for water versus other substances, as we talked about. When it does come together in that solid phase, creates a lot of open volume and thus a smaller density than in the liquid phase, which is an unusual sort of property for a particular substance. And hydrogen bonding, again, is basically that positive negative attraction that we talked about between the positive hydrogen in one and the negative oxygen in the other, gives us that classic opposites attract. Again, our intermolecular force there, our relatively strong one, which is hydrogen bonding. And because of sort of that property, water does expand when it freezes because of all that empty volume, right? And if you ever, for example, wanted to cool down, say, a soda in a can, right, or something like that, and you like, I'll put it in the freezer really quick, you know, and then you forget about it, and you come back, and when you take out the can, the bottom is sort of pushed out, sort of expanded, and that's because all the water molecules in there have now went into the solid phase and expanded, and obviously it had nowhere to go but push out the can's bottom, right? And you got the cool wobbly can and all that good stuff. And again, same thing, if you put water in frozen, let's say a glass jar, it may expand and break the jar as well. And again, because of that increase in volume that occurs here in the solid phase, we do see that decrease in density, and it will start to expand. Now, when we talk about water, we usually think of the density of water as 1 gram per mil, and that's usually, almost standard, the value that we use for water, and that's liquid water, by the way. And density does change with temperature. So the density of liquid water will be different depending on the temperature that there is. And its greatest density is about 1 gram per milliliter, and that's about 4 degrees Celsius. And anything less than that, will be obviously lighter in terms, or lower in terms of the density, and will sort of float. And that's really important, for example, for how water, for example, freezes in, say, lakes or something like that, right? So water in a lake actually freezes from the top down as opposed to from the bottom up. And that's really important, obviously, for like fishes and stuff like that that's maybe living in the lake. If it froze from the bottom up, everybody would be frozen there, and that wouldn't be so good. But since it actually freezes from the top down, what it essentially will do is create sort of a insulated layer up on top that actually will prevent the lower layer from freezing altogether. And that's good for obviously the wildlife that's living in the lake. It won't freeze and stuff like that. And that's because the colder water is less dense. The colder water will actually come to the surface. When it reaches the surface, it will actually start to freeze. The warmer water in that case will actually drop lower. The 4 degrees water will sort of drop lower because it's more dense and come to the bottom. And what that does is it creates something like this where, again, like I said, sort of the colder water works its way to the top, and it will start to freeze and create this layer of ice, right? And our warmer water will work its way sort of to the bottom and still remain in the liquid phase. And that's good for our good friend here, Melvin the fish. Although he does look like he's in an ice cube, he's actually not. We'll pretend he's not. He's, floating around free in there. And again, it sort of creates this layer, which is why, right, you can fall through the ice in certain cases, right? And then end up in very, very cold water underneath, because technically underneath it is still liquid water, super cold liquid water, probably in a lot of cases. But it sort of creates this insulated layer on top. And again, kind of protects the rest of it from continuing to freeze. So in terms of lakes and stuff like that, again, it sort of freezes from the top down, and that's really good for sort of, wildlife that's living there. So let's talk a little bit about types of solids here, now that we sort of talked about liquids. And solids, right, are very rigid. They're very hard to change the shape of it. Again, you can't transmit pressure in all directions. And there's really two types of solids that we oftentimes will talk about. One's a crystalline solid, and that is a very ordered arrangement of particles in sort of its three-dimensional form or its crystal form. Things like ionic compounds, they have basically, as we'll talk a little bit about, really long range order, which means when they come together in the solid state, they have these very ordered repeating patterns as to how they sort of come together. And when we talk about something that's an ionic compound, basically they arrange themselves where all this positive ions and negative ions come together in this nice ordered pattern. There's also amorphous solids, which exhibit very long range, very little long range order. So they don't have that sort of very repeatable pattern that occurs. Things like glass and polymers are sort of amorphous solids. And that brings us to what is sometimes referred to as a crystal lattice. And that's when, basically allowed to cool slowly, particles will again arrange themselves in that sort of solid state to maximize those attractive forces. So a little bit like we were talking about with our intermolecular forces and so forth, or just our intramolecular forces as well. When things come together in sort of the solid state, everybody's really close to each other. So they do try to, like we talked about, maximize areas where sort of positive things and negative things are near each other, because they do like to be near each other. But when you do get all these things coming together at once, no matter what you do, you are going to get areas where positive guys and positive guys are near each other, which they don't really want to be. You also have some negatives and negative guys near each other, and they don't want to be. So typically in solid states, they're sort of move around a little bit to sort of maximize sort of the location of everybody where we sort of really see a lot more positive guys near negative guys. And although we still have positive areas near positive areas and negatives near negatives, they're sort of minimized. So we try to keep that to a minimum and have more of the positive negative attraction. And again, that allows everybody to come together in sort of the solid state. And I think we will stop here because then we're getting into something that we needed a little bit more than like a minute to talk about. So we will stop lecture here today, and we'll pick up obviously tomorrow. Today in lab, we are doing part 1 of a gas experiment. I want to say molar mass of methane, I want to say is I think the title. I think it should be experiment 11, I believe it should be. Yeah. So experiment 11, part 1 today. So like we've been doing, we're going to do part 1 today. I believe part 2 tomorrow. We'll talk about part 1, what's going on, and then sort of the calculations involved in part 1. And then obviously you can go off and do part 1. Any questions on any of that stuff? Okay, I'll see everybody in about 20 minutes. If you haven't done so, make sure you do right here, and then we'll see everybody in 20 minutes. You know what? Let me double check. I want to say it's the new one. I think I published both by accident, so I think it should be the new one. I'll double check when I look at it. I just don't know off the top of my head. Okay, I'll see everybody in about 20 minutes.